The universe is a vast and silent place, or so it seems. When we look up at the night sky, we see a beautiful, peaceful canvas. Billions of stars twinkle with a steady, reassuring light. They appear calm, distant, and eternal. But this stillness is an illusion. The cosmos is actually a theater of unimaginable violence and drama. It's filled with events so powerful they beg a belief. Stars are born in fiery nurseries of gas and dust. Galaxies collide in slow, majestic dances that span millions of years. And in the darkest corners of space, some stars are not living peacefully. They're locked in a desperate, deadly embrace with a monstrous companion. These are not the gentle stars we imagine. They're part of a cosmic horror story. A tale of vampirism on a stellar scale. Imagine a star, much like our own sun, slowly having its life force drained away. Its outer layers are stripped from its surface, pulled across the void by an unseen force. When we think of monsters, we often imagine creatures from fiction. Vampires, werewolves, and ghosts that haunt our stories and films. But the universe has its own monsters. They are far more real and infinitely more powerful than anything from our nightmares. These are not living beings in the way we understand them. They are the extreme endpoints of stellar evolution. They are the collapsed corpses of giant stars that have ended their lives in spectacular supernova explosions. What remains is an object of incredible density and gravity, an object so extreme it warps the very fabric of space and time around it. There are two main types of these cosmic monsters. The first is the neutron star. Imagine taking a star more massive than our sun and crushing it down, squeezing it until it is only the size of a city, maybe 20 kilometers across. A single teaspoon of neutron star material would weigh billions of tons. Its gravitational pull is staggering. The second type of monster is even more extreme. It's the most mysterious object in the entire universe, a black hole. Here, gravity has won the ultimate battle. Surrounding this point is a boundary known as the event horizon. This is the point of no return. Anything that crosses it, including light itself, can never escape. The story of an X-ray binary is a story of a relationship, a very close and very destructive relationship. It begins with two normal stars, born together from the same cloud of gas and dust. They orbit each other in a graceful, stable dance that can last for millions or even billions of years. They are a binary star system, a common arrangement in the cosmos. But one of the stars is destined for a more dramatic fate. It is more massive than its partner. Because it is more massive, it lives its life faster. It burns through its nuclear fuel at a furious rate. While its smaller companion is still in the prime of its life, the larger star begins to die. It swells up to become a red giant, its outer layers expanding enormously. Then, its life ends in a cataclysmic supernova explosion. The explosion is so bright it can briefly outshine its entire host galaxy. For a moment, it is one of the most brilliant things in the universe. But when the light fades, something new is left behind. The collapsed core of the massive star now remains, as a neutron star or a black hole. As the star expands, it approaches a critical boundary in space. This boundary is called the Roche lobe. You can think of it as a gravitational teardrop shape surrounding each star in a binary system. Inside its Roche lobe, a star's own gravity is dominant. But if the star expands beyond its Roche lobe, its outer layers of gas will cross over into a region where the companion's gravity is stronger. This is the point of no return. The gas is no longer bound to the donor star. It is captured by the immense gravitational pull of the neutron star, or black hole. Once the donor star fills its Roche lobe, a stable and continuous flow of gas begins. A river of stellar material, mostly hydrogen gas, is siphoned from the donor star. It pours through the point of gravitational balance between the two stars, known as the inner Lagrangian point. The stolen material does not simply crash onto the surface of the compact object. Because the two stars are orbiting each other, the entire system is spinning. The stream of gas from the donor star has angular momentum. Instead, it is deflected sideways, entering into orbit around the neutron star or black hole. This orbiting material flattens out due to collisions and friction within the gas itself. This is the famous accretion disk. The accretion disk is where the real magic happens. As the gas spirals inwards, an enormous amount of gravitational potential energy is converted into heat. This process heats the gas to temperatures we can barely imagine. At these extreme temperatures, the material in the disk glows with ferocious intensity. But it does not glow in the visible light our eyes can see. It shines most brightly in high-energy wavelengths, primarily X-rays. The process of star vampirism begins not with a bite, but with an invisible, inescapable pull. In a young X-ray binary, a normal star and its compact companion can actually orbit each other peacefully for millions of years. But the living star is on its own evolutionary journey. As it ages, it burns through the hydrogen fuel in its core and starts to swell. It transforms into a red giant. Now, imagine a gravitational field of battle drawn in space between the two objects. Each star has its own zone of influence, a region where its gravity reigns supreme. The critical moment arrives when the expanding star finally overfills its Roche lobe. Its outer atmosphere pushes past the boundary. This gas has now crossed a point of no return. Once the donor star begins to shed its skin, a remarkable structure forms between the two celestial bodies. A stream of gas, a veritable river of stellar material, flows from the living star towards the dead one. This isn't a gentle trickle. It's a torrent of superheated plasma composed mostly of hydrogen and helium. It travels at incredible speeds, pulled by the immense gravity of the compact object. This river of gas doesn't flow in a straight line. The entire system is in constant motion, with both objects orbiting a common center of mass. Because of this orbital motion, the stream of gas carries with it angular momentum. It means the material can't simply fall directly onto the neutron star or black hole. Instead, as it gets closer to the compact object, the stream is deflected sideways. The path of the stolen gas becomes a graceful yet deadly spiral. The stream of stolen gas can't orbit the compact object forever as a simple river. As more and more material flows from the donor star, it starts to collide with itself. The spiraling stream catches up with its own tail. This friction and these collisions are what cause the stream to spread out and flatten. It's forced into a disc-like shape. This is the birth of the accretion disk. This disk is a celestial whirlpool. The different parts of the disk rotate at different speeds. The inner regions, closer to the immense gravity of the central object, orbit incredibly fast. The outer regions move much more slowly. This difference in speed creates immense friction within the disk. As gas particles rub against each other, they heat up. The temperatures within the accretion disk are staggering, reaching millions of degrees Celsius. The final moments for the stolen matter are the most violent of all. As the plasma spirals through the inner regions of the accretion disk, it is accelerated to phenomenal speeds and heated to its peak temperature. This is where the vast majority of the X-rays are generated. The intensity of this X-ray emission is truly awesome. A single X-ray binary can be millions of times more luminous than our sun. The ultimate fate of the matter depends on the nature of the cosmic vampire at the center of the disk. If the compact object is a neutron star, the plasma finally crashes onto this unimaginably dense crust. If the central object is a black hole, the matter reaches the event horizon. It slips across this boundary and disappears from our universe forever, its final burst of X-rays being its last signal to the cosmos. At the very center of every X-ray binary's violent drama lies the engine, the cause of all the chaos. It is the object whose incredible gravity orchestrates the entire cosmic performance. There are two main culprits we find lurking at the heart of these systems. The first is a neutron star. The second, even more extreme, is a black hole. Astronomers can often tell which kind of monster they are looking at by studying the details of the X-ray light. The mass of the object is a key clue. If the compact object weighs more than about 3 times the mass of our sun, it is too massive to be a neutron star. In that case, we know we are dealing with a black hole. Let us first consider the neutron star. This object is a marvel of extreme physics. It is born from the fiery death of a star between about 8 and 20 times the mass of our sun. The pressure is so great that it overcomes the forces that keep atoms apart. Protons and electrons are squeezed together to form a sea of tightly packed neutrons. What is left is a sphere perhaps only 20 kilometers across, the size of a city, yet it contains more mass than our entire sun. A single teaspoon of its material would weigh billions of tons. When a neutron star is the vampire in an X-ray binary, the stolen gas crashes onto the neutron star's crust. This continuous bombardment heats the surface to millions of degrees. Now we turn to the second, more mysterious suspect, the black hole. When a star more than about 20 times the mass of our Sun dies, its core collapse cannot be stopped by any known force. It crushes down past the neutron star limit, collapsing forever into a point of infinite density called a singularity. Surrounding this point is the event horizon. In an X-ray binary, a black hole companion shapes the system in a unique way. However, there is no solid surface for the material to crash onto. Black hole X-ray binaries are also often associated with the most powerful jets. These relativistic jets are a sign of a truly powerful central engine. So how do astronomers tell these cosmic monsters apart? The first and most important tool is measuring the object's mass. By observing the orbit of the normal donor star, we can calculate the mass of its unseen companion. The pattern of the X-ray light itself provides crucial clues. A regular repeating pulse is the smoking gun for a spinning neutron star with magnetic hotspots. Another powerful indicator is the presence of explosive bursts. Neutron star surfaces can act like giant powder kegs, triggering runaway thermonuclear explosions. By combining all these methods, astronomers can build a clear profile of the monster lurking at the heart of an X-ray binary. Our journey into the gallery of cosmic vampires must begin with a true pioneer, a system that changed our understanding of the universe forever. It is called Cygnus X-1. In the early 1960s, astronomers launched rockets equipped with X-ray detectors above Earth's atmosphere. They were stunned to find incredibly bright points of X-ray light dotted across the sky. They found that it coincided with a massive, hot, blue supergiant star. But the star itself was not hot enough to produce such powerful X-rays. Something else had to be there. By studying the light from the blue supergiant, astronomers noticed it was wobbling. It was being pulled back and forth by the gravity of an invisible companion. Using the star's wobble, astronomers could calculate the mass of this invisible partner. The result was astonishing. The unseen object had a mass of around 15 times that of our Sun. This was far too massive to be a neutron star. Physics dictated that an object that massive and compact could only be one thing: a black hole. This was a landmark moment. While Cygnus X-1 was the first confirmed black hole, it was not the first X-ray binary ever discovered. That honor goes to another giant of the X-ray sky, a system named Scorpius X-1. Its discovery in 1962 was a complete accident. A team led by physicist Riccardo Giacconi launched a rocket to look for X-rays coming from the moon. The rocket's brief flight failed to detect any X-rays from the moon. But as the detector scanned across the sky, it found something completely unexpected, a phenomenally bright source of X-rays. This source was 1,000 times brighter in X-rays than anyone had predicted. This single accidental discovery opened up a whole new field of science: X-ray astronomy. Some X-ray binaries have names that are simply unforgettable. Few are more evocative than the Great Annihilator. This formidable system lurks near the supermassive black hole at the heart of our Milky Way galaxy. It earned its dramatic nickname for a very good reason. Something near the center of our galaxy was creating a fountain of antimatter. When electrons meet positrons, they annihilate each other in a flash of energy. The Great Annihilator is a black hole X-ray binary that appears to be a particularly efficient factory for producing antimatter. The leading theory is that the powerful jets blasting away from the black hole's accretion disk are the source. X-ray binaries are not just places where matter is consumed. They are also cosmic particle accelerators, capable of creating exotic materials like antimatter and flinging them across space. We have journeyed through a hidden realm of the cosmos, a place of stellar vampires and cosmic ghosts. We have seen how pairs of stars can become locked in a dramatic dance of life and death. This cosmic theft is not silent. It screams into the void with a light our eyes cannot see. A brilliant, ferocious torrent of X-rays that tells a story of unimaginable power and violence. These systems are far more than just celestial horror stories. They are invaluable laboratories for understanding the fundamental laws of physics. They allow us to study matter under conditions impossible to replicate on Earth. We can see the effects of gravity so strong that it warps the very fabric of space-time. X-ray binaries are the ultimate stress test for our most cherished scientific theories. we can confirm that these strange predictions of Einstein's theories are not just mathematical phantoms. They are real, physical objects that populate our galaxy in their millions. They have unveiled a hidden layer of the cosmos, one that is dynamic, violent, and far more energetic than the calm night sky would suggest. The story of X-ray binaries is not just one of death and destruction. It is also a story of creation and renewal, a vital part of the great cosmic ecosystem. The powerful winds and jets that erupt from X-ray binaries enrich the interstellar medium with heavier elements forged inside stars and accretion disks. They inject huge amounts of energy into the galaxy, stirring up the gas and potentially triggering the formation of new stars. The death throes of one system can become the spark that ignites a new generation. X-ray binaries are the progenitors of universe-shaking events. When compact objects merge, they create gravitational waves that we can now detect on Earth. So the cosmic vampire is not just a monster, it is a recycler. It takes material from one star and redistributes it, transforming it and injecting it back into the galaxy with explosive force. It is a beautiful, intricate, and violent dance that connects generations of stars across billions of years, ensuring that the universe is never static, but always changing. Our understanding of X-ray binaries has grown immensely since that first accidental discovery 60 years ago. With each new generation of telescopes, we peel back another layer of the mystery. We can now see these systems with incredible clarity, mapping the flow of gas, timing the flicker of light from the edge of a black hole, and tracking the immense power of their jets. The future of X-ray astronomy is bright. New observatories are being planned that will have even greater sensitivity and sharper vision. They will allow us to find fainter and more distant X-ray binaries. They will allow us to probe the region just outside the event horizon of a black hole with unprecedented precision, testing Einstein's theory of general relativity in the most extreme environment possible. So the next time you look up at the seemingly peaceful night sky, remember the hidden drama playing out among the stars. Remember the stellar vampires and their silent, screaming feasts. The study of X-ray binaries is a journey to the edge of what is known, a true endless frontier that promises discovery and wonder for generations to come.